Welcome to our deep dive into the neural network's learning process, where today's focus is on backpropagation. Pictured here is an artistic representation of a neural network, symbolizing the intricate and layered structure of interconnected nodes, a fitting metaphor for the complexity and beauty of machine learning. Backpropagation is the backbone of how neural networks learn from data. It's a mathematical method for adjusting the weights of connections in the network based on the error rate of output compared to the desired result. Through iterative adjustments, backpropagation fine-tunes the network's predictions, leading to improved accuracy over time. In the coming segments, we will unravel how this process works, why it's crucial for artificial intelligence, and how it propels machines from mere data processors to entities capable of learning and evolving. Stay tuned as we explore the layers, nodes, and connections that compose the learning mind of a neural network. On our screen is a schematic of a neural network, alongside a brief overview of its operational mechanics. Neural networks are computational architectures that mirror the human brain's network of neurons. They are composed of layers of nodes, each layer capable of performing complex computations. By simulating the synaptic connections of biological neurons, these networks process information and make decisions. The training of a neural network is a structured and iterative process that involves several key steps. Forward propagation. This is the initial phase where input data is fed into the neural network. Each input node receives a value, which is then processed through various hidden layers. As data moves through the layers, each node applies a set of weights to its inputs, sums them, passes them through an activation function, and forwards the result to the next layer. Loss calculation. After forward propagation, the network produces an output. This output is compared to the desired outcome using a loss function, which measures the discrepancy between the predicted value and the actual target value. The result of this function quantifies the error and provides a concrete goal for optimization. Backpropagation. Here lies the essence of learning. In this critical phase, the network adjusts its weights. Starting from the output layer, the gradient of the loss function is calculated, and this information is propagated backward through the network's layers. This step is crucial as it informs each node how it should adjust its weights to minimize the error. Iteration. Training a neural network is not a one-off task. The network iterates through the cycle of forward propagation, loss calculation, and backpropagation multiple times, each pass using the updated weights from the previous cycle. Through these iterations, the network's performance on the training data continually improves. The overarching objective of this iterative training process is to minimize the loss function. By doing so, the network refines its weights and biases to the point where it can accurately predict outcomes or make decisions based on the input data it receives. In this segment, we turn our attention to the cost function, a pivotal concept in the realm of neural networks and machine learning. The cost function, also known as a loss function or error function, quantifies the difference between the predicted output, BEI hat, of the network and the actual target value, Y. Why is the cost function so crucial? It serves multiple purposes, guides training. It acts as a beacon for the training process. By calculating the gradient of the cost function, we can determine the direction in which to adjust the weights, WI, to decrease the error. This gradient points to the steepest ascent in the loss landscape, and by stepping in the opposite direction, we can find the path towards the lowest error. Performance metric. The cost function provides a tangible measure of the network's performance, A lower value indicates better accuracy in predictions, and tracking this over time helps us understand how well the network is learning. The process of tweaking the network to minimize the cost is known as optimization. Gradient descent is one of the most widely used optimization algorithms. It iteratively adjusts the weights to minimize the cost function until the changes are imperceptibly small, indicating that the model has reached a point of convergence. The key takeaway here is the importance of a well-chosen cost function. It needs to be appropriate for the specific problem the network is trying to solve. When properly minimized, it ensures that the neural network is effectively learning from the data and can make accurate predictions. We now arrive at a fundamental concept in neural network training: gradient descent. This visualization represents a cost function, f of x equals x squared, which is a simple quadratic function used to illustrate the concept of finding a minimum value. The curve dips towards its lowest point, the vertex of the parabola, which in optimization terminology is referred to as the global minimum. The formula displayed is the mathematical representation of the gradient descent algorithm. Here's what it means. Wx represents the weight we are trying to optimize. Alpha denotes the learning rate, a hyperparameter that controls how much we adjust Wx of with each step. It's critical to set the learning rate to an appropriate value. Too large and we may overshoot the minimum. Too small and the training may become impractically slow. The term in red is the partial derivative of the error with respect to the weight Wx, also known as the gradient. This tells us the slope of the cost function at the point Wxe. The process of gradient descent involves iteratively adjusting Wx by taking steps proportional to the negative of the gradient. This is akin to descending down the slope of the curve until we reach the bottom, the point where the cost is minimized. In the context of a neural network, gradient descent is used to find the set of weights that leads to the smallest possible error, ensuring the outputs of the network are as close as possible to the expected values. By continuously iterating this process across all the weights within the network, we effectively train the network to understand and process the underlying patterns in the data. This slide brings us to the core of the neural network training process: backward propagation, commonly referred to as backpropagation. It's the mechanism by which a neural network learns from its errors and updates its weights accordingly. Here we see the formula W new equals W old minus alpha times the derivative of the loss function with respect to weight, which succinctly captures the essence of backpropagation. Let's break it down. W old is the current weight prior to the update. Alpha represents the learning rate, determining the size of the step we take in the weight space. During backpropagation, the error is computed at the output and is propagated backwards through the network, hence the name. This is done by applying the chain rule of calculus to compute the gradient of the loss function with respect to each weight. In essence, it calculates how much each weight contributed to the error. This slide illustrates a single layer with inputs x and y and output z. The partial derivatives, derivative of z with respect to x and derivative of z with respect to y, represent the local gradients at the node, and derivative of L with respect to z is the derivative of the loss with respect to the node's output. By multiplying these values, we obtain the gradient of the loss with respect to the inputs, which tells us how much the error will change with respect to a change in each input. This information is used to update the weights and biases in the network. The beauty of backpropagation is in its recursive application, allowing a network with many layers to learn efficiently. Each layer's weights are updated to minimize the loss, leading to a more accurate model over time. As we continue, we will examine how this method is applied in practice and the various factors that can affect its performance, such as the choice of activation functions and the initialization of weights. As we delve deeper into the mechanics of neural network training, we are presented with the backpropagation algorithm, a structured multi-step process that enables a network to learn from data. Let's walk through the steps of this pivotal algorithm. Forward pass. The journey of input data begins here as it travels through the neural network's architecture. Each layer processes the data, passing its output forward as the input to the subsequent layer. This sequential computation continues until the final layer produces the network's prediction. Compute the loss. Once the forward pass is completed, the network's prediction is evaluated against the actual target values using a loss function. This function measures the network's performance by quantifying the error in its predictions. Common loss functions include mean-squared error for regression tasks and cross-entropy for classification tasks. Backward pass. This is where the network learns from its mistakes. The backward pass calculates the gradient of the loss function with respect to each weight in the network. By applying the chain rule of calculus, the algorithm computes how changes in each weight affect the loss. This computation begins at the output layer and proceeds backward through the network's hidden layers. Gradient descent. With the gradients in hand, the network updates its weights. This step is guided by the principle of gradient descent, which dictates that weights should be adjusted in the direction that most reduces the loss. The size of these adjustments is controlled by the learning rate, a crucial hyperparameter. Iterate. The process is iterative. The network repeatedly executes forward passes, computes loss, performs backpropagation, and updates weights until the loss is minimized to a satisfactory level, indicating the network's predictions are as accurate as possible. Tuning. Finally, there is an optional but often necessary step of tuning hyperparameters. Adjustments to the learning rate, network architecture, and other parameters can significantly enhance the network's learning efficiency and overall performance. Through these steps, the backpropagation algorithm equips neural networks with the ability to learn complex patterns and make accurate predictions, continually improving through experience, much like humans do. This is the bedrock upon which modern machine learning and artificial intelligence are built. While backpropagation is a powerful algorithm for training neural networks, it is not without its challenges. Let's explore some of the key obstacles that can arise during the process. Vanishing gradients. This occurs when the gradients become progressively smaller as the backpropagation algorithm moves from the output layer to the input layer. It's especially prevalent in deep networks with many layers. Certain activation functions, such as the sigmoid function, exacerbate this issue because their gradients can be very small. Consequently, weights in the earlier layers may receive minimal updates, leading to a significant slowdown in the training process or even complete stagnation. Exploding gradients, the counterpart to vanishing. Exploding gradients happen when large error gradients accumulate and result in very large updates to the weights during training. This can cause the network's weights to oscillate or diverge to extremely large values, making the network unstable. Weight initialization. The initial setting of the weights can significantly influence the network's ability to learn. Poor initialization can lead to vanishing or exploding gradients. Implementing a thoughtful strategy for weight initialization, such as Xavier or He initialization methods, can help mitigate these problems. These methods adjust the weights based on the number of inputs and outputs from a layer, providing a balanced starting point that neither amplifies nor diminishes the gradients too much as they pass through the network. It's important to address these challenges to ensure the successful training of neural networks. Researchers and practitioners use various techniques, such as choosing different activation functions, e.g., ReLU, employing batch normalization, gradient clipping, or changing the network architecture to overcome these hurdles and create models that learn efficiently and effectively. In addition to the previously discussed challenges, there are several other issues that can impede the efficiency and effectiveness of backpropagation in training neural networks. Overfitting. This occurs when a model learns the details and noise in the training data to an extent that it negatively impacts the performance of the model on new data. It's akin to memorizing rather than understanding. Overfitting can be mitigated through regularization techniques that penalize overly complex models, dropout methods that randomly ignore units during training, or simply by expanding the dataset to provide a more comprehensive learning experience. Local minima and saddle points. In the complex landscape that a neural network's loss function represents, there are numerous points where the gradient is zero. These can be local minima or saddle points, where the model stops learning because it appears to be at an optimum, even though it may not be the global minimum. Advanced techniques like stochastic gradient descent and alterations to the learning rate schedule can help the model to bypass these points and continue searching for the global minimum. Computational intensity. The backpropagation algorithm requires substantial computational resources, particularly for deep networks with large numbers of parameters. This computational demand can be addressed by using more efficient hardware like GPUs, graphics processing units, or TPUs, tensor processing units, and through the use of parallel computing techniques that distribute the computational load. Numerical stability. The use of floating-point arithmetic in the calculations can introduce round-off errors that may lead to numerical instability. This is especially problematic when dealing with very small or very large numbers. Techniques like batch or layer normalization help to maintain numerical stability by ensuring that the inputs to each layer have a consistent and controlled distribution. Addressing these challenges is crucial for the successful application of neural networks across a variety of tasks. It requires a combination of good practices in model design, careful hyperparameter tuning, and leveraging advancements in hardware and optimization algorithms. As we conclude our exploration of backpropagation in neural networks, we look forward to the next installment where we will delve into convolutional neural networks, CNNs. These powerful architectures are particularly well suited for processing and understanding visual data, making them a cornerstone of modern computer vision applications. In our upcoming video, we'll uncover the layers and mechanisms that allow CNNs to automatically and adaptively learn spatial hierarchies of features, from edges and textures to more complex patterns. Stay tuned as we unravel the convolutional layers, pooling layers, and fully connected layers that empower these networks to excel in tasks such as image and video recognition, image classification, and medical image analysis.